Okay, so welcome Jordan and Victor and Caesar and Jesus and Ralph and Bradley. Thanks for coming. And let me share my desktop and I'll talk about the plan today. Okay, so here is the plan. And as always, I'll start out with any questions you might have after I go over what we're doing today. And then I'm going to do something actually out of my list last time, but I didn't get to it. And that's fine because I got ahead so that we can do what we need to do today. And that is a non-example of a vector space. So if you remember last time we talked about what is a vector space, and we realized three big examples were Rn, vectors in Rn, and matrices that are m by n matrices, and polynomials of degree n or less. Those were three main ones, and there's a whole lot of others too. Functions are another one. So those were examples, but I think it's helpful to also see what isn't a vector space, where things can go wrong. And I'll give you an example of a non-example. Then after that, we're going to get into the uniqueness theorem. And it's a little bit strange looking because you're going to look at it and you're going to say, well, that's obvious. And then you have to think about it and say, well, why is it true? And then it's harder to prove than to realize, to believe. Very easy to believe it's true. So we'll see that. And similarly, we're going to have another theorem that's called the cancellation theorem. And same idea. It's obvious because it's something you've been doing all your math life, but we're not doing numbers, we're doing vectors. So just to note, we'll have that cancellation theorem. And then after the cancellation theorem, then what we're going to do is we're going to basically revisit the class. It's actually kind of a nice review for the final because we're going to go back to the beginning and we're going to give you, I'm going to rewrite the definitions I wrote for matrices. And I purposely, when I did it for matrices, didn't ever write a matrix so that I can just say, remember that definition? It hasn't changed. So we're going to be looking at what it means to be a linear combination. And the nice thing is we've already talked about it. What is it? What is a linear combination of vectors? And we'll have a definition. It's the same definition we've already had. And then we'll get into what does it mean for this to be the span of a set of vectors. And the good news is we've already had it, but we didn't have it in this reference before. So today, this section 9.2 is all about taking what we already had as a special case with Rn and writing it down and realize it works for general vectors also. So we'll also talk about not just the span of a set, but we're going to look at the other word for span, and that is what does it mean for a set to span a vector space? So we'll look at span. And then finally, we'll talk about the exam. So hopefully you better all know, when does the exam happen?
1 o'clock on Monday.
Yeah, 1 o'clock on Monday. So in 72 hours, just let you know. Okay, actually 71.95-ish hours because it's already a little past 1 now. So I'll talk about the exam. I obviously won't show you the exam, but talk about what to expect. And then I'll also take any questions you want, or if you want to see sample problems, we can do that. So again, anything since the last exam is fair game for this exam. So that is the plan for today. So are there any questions you might have about homework or about anything else other than the exam, because we'll have plenty of time for questions when I go over the exam.
A quick question I have, vector spaces pertaining to functions, do the domain and ranges dictate the dimension of the vector space?
So the domain and the range dictate the dimension. So I don't know if dictate is the right word, but from the domain and the range. So first thing, a domain and range, I think you're confused between a linear transformation and a vector space. Or you mean the domain of the function?
Yeah, the function
Okay,
itself.
so first thing, a vector, so you're thinking about the vector space of functions, right? That you're talking about?
Yeah.
Okay, so it turns out, and I didn't prove this before, and in fact, we don't even have a definition of dimension yet. Do you realize that?
Yeah, because
So I
there's
can't prove it because
yeah.
if we don't know what it is, you can't prove it, right? It turns out, and just because I didn't prove it or haven't written it down doesn't mean it doesn't exist. Just means we haven't gotten to it yet, which we will after the exam, by the way. It turns out that the dimension of the vector space of all functions is infinity. Okay, but then it gets deeper than that, which we're not going to do in this class, but it's actually a non-countable infinity. So it's actually a very high level of infinity. So I don't know if that was exactly what you wanted for your question. So the domain and range, first thing, if you're talking functions, there's just functions. But if you're talking about, say, functions from R1 to R2, R1 to R1, good old fashioned functions that you learned first, they have infinite dimensional. Does that make sense?
Yeah.
Okay. If you did a function on the numbers 1 and 2, then you're going to have a finite dimensional. So if you're going to send 1 and 2, sorry, 1 and 2 to 1 and 2, and that's all you're going to do, and you're going to look at those functions, those can be finite, but you don't usually deal with those functions. Does that make sense?
Yeah. Thank you.
Usually deal with functions from the real numbers or from R2, and those all have infinite dimension. Okay. Victor had a question about number 14. So let me go and find number 14 and put it into the Word document. So it takes a moment to do that. Oh, 114 is a short one. So I still got to get it though. Okay, so this is the 14 you want, right? So since lambda is not equal to mu, it follows that x dot y equals 0. Okay. Let me look at, there might have been a prelim of that. Let me look at the prelim. Yeah, so they're really saying is a little, kind of the wording is a little weird. It really shouldn't be since. It should be prove that if lambda is not equal to mu, then x dot y equals 0. Then x dot y equals 0 when x and y are the associated eigenvectors of the eigenvalues lambda and mu. Does that make sense that that's what they're asking for? Okay, because I can't imagine them asking for anything else.
Yeah.
Okay, so now we have to go prove that. So we have to show that x dot y is equal to 0. Well, first thing is, and hopefully you're used to this, is that whenever you want to show inequality, start on the left and hopefully you get to the right. Is that clear? So let me start on x dot y. So x, I'm going to use lowercase because it's easier to type, if that's okay. X, and then we got a dot. And dot are an operators, I believe. Just a minute. There it is, dot y. Okay, equals. Okay, we're hoping it's equal to 0, but we need to show it, right? So we look at x dot y and we say, what is that equal to? Well, the idea is that x is the eigenvalue, eigenvector associated to the eigenvalue lambda. Any questions on that? So we know x dot y equals. So x now is, well, we know that AX equals lambda X. Is that clear?
Yeah.
Okay. So we know that XY is going to be equal to A. It's going to be equal to A times 1 over lambda X. I'm going to pull the lambda out. 1 over lambda. Let me grab a lambda. There we go. So XY is equal to 1 over lambda times X times, sorry, AX dot with Y. The dot is always hard to get to, but I'll get there. Any questions so far? Okay, so we know that's true, right? Okay, but we also know, and we can write this out, is that X dot Y has another way of writing it. So let me rewrite this. We could say X dot Y is going to be 1 over mu times X dot AY. Sorry, it takes a while to get to that mu. Any questions on that? Okay, well, now we could do, hopefully it's obvious. What could we do with these two equations?
Made them equal.
Yes, so we could set them equal to each other. So let's do that. So I can say that 1 over mu X dot AY is equal to 1 over lambda AX dot Y. Okay, and by the way, I'm assuming X and Y are non-zero, but if there's 0, it's actually easier. If there's 0, what can I do? So if, or one of them is 0, if lambda is 0, then what can I do? Then what do you know? Then I can apply A to both sides. And we know AX is equal to 0. And then you can say you get AX dot Y equals 0. And then A time XY equals 0. And then XY must be 0. Okay. But if they're not, then we do this. Now what can I do? Any thoughts? We had a theorem about this. When you had AX dot Y, how can I change that? Do you remember what I can do?
Change X with Y.
You can't change X with Y, but you can move the A in. And we had a theorem about that before. Do you remember that theorem?
Oh, yeah.
But that's good because now we know that X dot Y equals 1 over mu X dot AY, and X dot Y equals 1 over lambda X over AY, right? Any questions on that? So what does that tell us? Okay, notice that X dot AY times 1 over mu is equal to X dot AY times 1 over lambda, but mu and lambda are different. So what can I say about X dot AY?
They must be different as well.
Different from what? So it's not different. So here's the thing. If I take a number and multiply it by 7, and I say I just took that number and multiplied by 8 and it got the same answer, what do you know about the number I'm thinking about?
It's 0.
It's 0. Does that make sense? So x dot ay is a number, and if I multiply it by 1 over mu, which is different than 1 over lambda, I get the same thing as if I multiply by 1 over lambda, right? So I'm taking a number and I'm multiplying by 2 different numbers, I'm getting the same answer. The only way for that to happen is for that to be 0.
Oh yeah.
Okay, so that means we're at 0. So since lambda is not mu, it takes time, lambda, sorry. Since lambda and mu are not equal to each other, there we go. We can conclude that x at y must be 0. Any questions on that? We must have gotten 0 when we took 1 over lambda times x dot ay. You lost any of that argument at all, or is that clear?
Now it's clear. Thanks.
Proofs are always that way, aren't they? Coming up with how to do it, that's hard. Okay, but again, not always, but often when you want to show inequality, start on the left, play around with it until you get to the right. And that's a good goal for equalities. It usually works, not always, but usually works. Okay, any questions on this? Okay, any other questions? Any other questions? Give you a minute to think, and then if not, we can move on. Okay, if there are no more questions, let's move on. And I have what I call a non-example. So here is the question I have for you. Okay, is consider the set of all elements in R2 such that addition is defined in this really weird way. So I'm going to change the definition of addition. And I'm going to say that if I have a vector x1, y1, and I add it to a vector x2, y2, or a point, however you want to call it, then I get x1 plus x2, which is what you expect. But instead of getting y1 plus y2, I get 2y1 plus 2y2. Looks reasonable, doesn't it? Okay, and scalar multiplication is defined as usual. If I take a constant times a point, xy, that's constant times x. That should be, sorry, comma, the constant times y. So I have a question for you. Is this a vector space? What do you think? Do you think this is a vector space? Chime in.
The addition to me just seems a little bit weird.
So what's your feeling? I'm not asking for proof yet. Is your feeling that it is or it isn't?
It isn't.
Right. If you ever see weird addition or weird multiplication, it usually doesn't work. Okay. There's a reason why we define multiplication and addition the way we do for all the things you're used to having. And the reason is so that you can have all the properties you want to have to make it a vector space. So our guess, and it's just a guess at this point, is that it's not. Okay, if you're guessing that it's not a vector space, but you want to confirm it, aka prove it, what do we have to do? What's the requirement to show something isn't a vector space?
It doesn't have one of the 10 properties.
Yeah, it doesn't have at least one of the 10 properties. So if we can find any of the 10 properties that don't work, then it's not a vector space. Whereas to prove something is a vector space, how many different things do you have to prove?
All 10.
10. Okay, so if you're not sure, then I would go for hoping it isn't, because it's a lot easier if you get lucky and it isn't. Whereas if you try and show they're all true, that could take a long time. Any questions on that idea? Okay, so let's see if we can find one of the properties that doesn't work. Okay, and of course, another reason why you would think it's not a vector space is, what's the title of this thing?
A non-example.
Non-example. That tells you, hey, it's probably not a vector space, or why would I do that to you, right? So this is not going to be a vector space, but now we got to think about it. So the first thing, and hopefully this is obvious, do you think it's going to be addition or multiplication that's going to be the problem?
Addition.
Yeah, it's going to be addition. So there's only 5 to look at as a problem. Do you see any of them that might not work? And we'll look at it again. What of the 5? What's your first choice of trying that may not work? And you got to remember the properties. There are 5 properties. Right? There was, if you remember, there was the addition has to keep within the set. You have to have commutativity. You have to have associativity. You have to have adding 0 gives you the same thing. Do you remember that?
I'm thinking number 4.
Which one's number 4?
0 plus v equals v for every v.
Okay, so let's try it. So again, all you have to show it doesn't work is one example. And what I recommend is make a somewhat random example instead of special examples. Does that make sense? So let's look at one. So let's go to 0 plus, now give me an example of a vector in R2 or a point in R2.
1, 2.
1, 2. See what happens. Okay. And by the way, what is 0?
The 0 vector in R2.
Yeah, 0 needs to be 0, 0. Okay, at least we think. We'll have to show that actually. And then we'll have to show that 0 really is 0. I know that sounds like a weird thing to say, but it's something you do have to show. What's 0 plus 1, 2? According to the definition of addition that I have here with this strange addition.
1 and 4.
Yeah, that's going to be 1, 4. Okay, so what that means is that 0, 0 is not the 0 vector. Okay, but here's the problem. There might be some other vector that's a 0 vector, right? Do you agree with that? This assumed that 0, 0 was the chosen vector to be the 0 vector. But how do you know 17, 12 is not the 0 vector?
We could test it.
Yeah, we can test it. And the easiest thing to do is go the other direction. So let's suppose we have, okay, and by the way, this is doing it your way. I'm going to show you an easier way, but I went with your way. If we have, let's say, A comma B, and we add it to C comma D, and we get A comma B. Let's see if we can find out what C and D are, right? Because to be the 0 vector, it means this must be true. Do you agree? But what is A plus B plus C plus D? I mean, AB plus CD. According to the funny definition of addition I've got here.
A
We
plus C,
Mm-hmm.
comma,
A plus what?
C,
A plus C, good. Comma.
2b plus
2B.
2b.
Yeah.
2b plus 2d. And that needs to be equal to AB, right? If it's the zero vector. Okay, now we're in R2. So that means A plus C is A. And 2b plus D equals B. Wait a minute. It shouldn't be 2b, it should be B plus 2D. It's 2b plus 2D. There we go. According to the definition. Okay, so that means 2b plus 2D equals B. Okay, so if A plus C is A, what do you know about C?
It's 0.
Yeah, C equals 0. These are numbers now. Okay, so we know that C equals 0. That's a given. Okay, so now we need to show that D is also 0. That's a little messier, isn't it? And you'll find out that you end up getting a anything could happen solution. So we actually don't know what the zero vector is because we can actually write this as D equals negative B over 2. Any questions on just solving that? Subtracting 2b and divide by 2. Okay, and right away, without even doing what we did before, this tells you that it's not a vector space, even without the adding 0, 0, and 1, 2, because 0, 0 may not be the zero vector. But the thing is, the zero vector can't be different for all vectors. This must be true for all vectors. Any questions on that? You have to get the same answer no matter what A and B are. You should always get the same answer for the zero vector, which we didn't. All right, that's the hard way. Anyone see the easier way? The easier choice of the 5? Because this is a proof, but this is a lot of work. Let's see.
V plus W equals W plus V.
Yeah, yeah, that one actually, if you do that, actually that's going to be true. Do you see that? Can you envision that? If you switch the ones and the twos, that's what we're looking at. You get the same answer. Okay, maybe I'll leave this at this one. Okay, so the hard way is to do both of these. The easier way is just say 0 is not unique. Do you see that? So in other words, this line here was never used. Do you see that? So that one can go away, and then easier is to say, therefore 0 is not unique, or therefore there is no zero vector. And if there's no zero vector, thus this is not a vector space. Any questions on that? Okay, let me do one more non-example just so we can kind of see it, another type of argument. So let's try another example. I'll call it example. How about V be the set of vectors. In fact, let's go polynomials in, I guess, of degree at most 2 with positive coefficient in front of x squared. And we're going to use the same addition and multiplication that we're used to. Is this a vector space? What do you think? In fact, let me write not positive, sorry, non-negative is a better word. I want 0 to be in it. So is this a vector space? What do y'all think?
No.
Okay, what do you think this, which one is violated? If you think it's not a vector space, then which one doesn't work? Which of the 10?
I'm thinking the first one.
The first one is that if I take 2 of these polynomials and add them, then I'm still get one of these polynomials. So if I take, let's write one down. So if I take ax squared plus bx plus c, and if I add that to dx squared plus ex plus f, do I get, and if a and e are, if a and d are positive or non-negative, and I add these up, do I get a non-negative coefficient in front of x squared?
Yes.
Yeah, so that's not a problem, right? And the degree is still no more than at most 2, right? So the first one's no problem. First one is true.
So probably b minus b equals 0.
One more time.
The number 5, b plus
Yeah. So
negative b equals 0.
yeah. So what you mean is there a additive inverse? Okay. Is there an additive inverse? And the answer is no. And what's an example? Make it easy.
X squared plus negative x squared.
Okay, so we're not doing x squared plus negative x squared because remember what we're saying is that does, so just look at x squared. And the question is, this does not have an additive inverse. Any questions on that? You have to prove that. So we could do that. There's an easier one though. That would take a little work to prove. What's the easier one? Okay, how about the first property under multiplication? Do you remember which one that one was?
AV is an element of V.
Yeah. So here's an example. Let's let A equal, I don't know, how about -3? And now give me a polynomial where the leading coefficient is non-negative. Any. Turns out any will work. Give me an example.
You can't.
No, just give me one.
I
There's
guess
lots of
maybe-
polynomials where the leading term's non-negative.
Okay, 1x squared.
Yeah, so how about x squared? And what is negative 3 times x squared?
Negative
About
3x squared.
Negative 3x squared. And that's not in it. Is not in V. But x squared was in V. Okay, so the first property of multiplication does not hold. Because the first property says that if you multiply by any constant, then you are still in the set. Is that clear? And here I just multiply by -3. I'm not in the set anymore when I started in the set. Don't you think that's easier? Any questions on this non-example? Okay, so now that we've done that, I'm going to move on to a big theorem. This is like one of the most interesting theorems is that it's so obvious, but proving it is not necessarily so obvious, but it's obviously true. Okay, so when I write theorem, I just mean suppose we have a vector space, then the zero vector is unique. Okay, so I'm not going to be able to find two vectors that work as a zero vector, two vectors that are different from each other. Similarly, negative V is unique. In other words, I'm not going to find two vectors that work as an additive inverse to a vector. Number 3 is if I take the number 0 and multiply by a vector, I get the vector 0. And number 4 is the number -1 times a vector is equal to the additive inverse of that vector. Do you agree that these are all like, of course they must be true? What do you think?
Yeah.
I mean, you look at these and you've been having this all your life, right? Is that a proof?
No.
No, that's not a proof. You can't prove it by saying, well, it has to be true because that's what I've learned all my life. That's not a proof. So we need to show, let's do number 1, because there's 4 things to prove. We need to show that the zero vector is unique. How do we do that?
Didn't we just sort of do that
When?
in our first non-example of a vector space?
Okay, first that was with an example.
Mm,
And proof by example is never a proof.
got it.
Yeah. So we can't use any properties, any example of a vector space to prove something about vector spaces. All we can use is the letter V and then the numbers 1 through 10. That's all we're allowed to do. Okay. So what does it mean to be 0? The zero vector.
All of your elements are 0.
Okay, so let's suppose your vector space is a space of functions. Tell me what you mean by all the elements are 0.
Maybe
All of the elements equal nothing. I don't.
What are elements, in other words?
it means that
Yeah, a vector doesn't have elements, is what I'm trying to say.
we are at the origin of the coordinate system.
Okay, a 5x3 matrix, is there a coordinate system there? Not really. We don't even have a coordinate system, and neither does the set of all functions. Yeah, so you can't even go there.
It's a magnitude of 0.
Do we have a definition of magnitude? What's the magnitude of x squared plus cosine x? So we don't even know what magnitude is. We don't have a definition of magnitude. So we have to go back to what 0 means. And what 0 means is that if we add it to a vector, you get what you started with. That's the definition of 0. It's the only definition of 0 for vector spaces. Is that clear? Okay, so you have to avoid going back to examples that you've lived with all your life. This is a 0 vector, not as in a number with a bunch of numbers with commas in between. Nothing to do with that. This just means that v plus 0 is equal to v. That's what it means to be the 0. Does that make sense? So that's the first thing, is understand what it means to even say 0. And that's what it means to say for all v plus 0 is v. Okay, so now the way to prove that it's unique is you prove it by saying, so to show something unique, you have to show that if you have 2 of them, what does that mean about the 2 of them if you have uniqueness?
They're not the same.
One more guess.
They are the same.
Yeah, uniqueness means that if you have 2 of them, they must be the same thing because there's only one of them. Do you see that? So let's say v plus x equal v, and v plus y equal v. What's our goal here?
To show that x and y are the same.
Yeah, we need to end up with y equals x or x equals y. Is that clear? Okay, so again, if you don't know what your goal is, you have no chance. So what can I do?
We set them equal to each other.
Yeah.
Okay, so let's write that down. That's v plus x equals v plus y. What can we do now? By the way, I'm following along because things sometimes work, things sometimes don't work.
Subtract v from both sides.
Okay, which property says we're allowed to subtract something from both sides? Is there a property that says we can subtract something from both sides?
No.
No, we don't have a property. It's not one of the 10 properties. We're only allowed to use the 10 properties. Is that clear?
This is one of the properties, though. It's like the additive property or something like that, right?
No, we don't have a property that says that we can subtract something from both
No,
sides.
not the subtraction. I mean, like if like a plus another thing equals b plus another thing, then b and a are equal.
Not one of the 10, no. That wasn't one of the 10. In fact, we're going to prove that one in a bit. In the next theorem is going to be that. So the answer is that didn't work. Does that make sense? So instead of setting them equal, we know that v equals v plus y. And we know that v plus x equals v. So what I can do is I can write, instead of that first v, I can write as v plus y. So we know that v plus y plus x equals v. We know that's true. Any questions on that? Okay, now is that going to help us?
Yeah.
How come?
Because y plus x must be 0 for v to equal v.
How come?
There's no other way to do it.
What if y plus x is, well, what is 0, by the way? Could there be 100 different zeros?
Could be, yeah.
Yeah, then that's not going to help. We're trying to prove that there's only one. Do you see that? So it doesn't help to call y plus x 0. Is that clear? Any questions on that idea? Okay. So that didn't quite work. Not the way you wanted it to, at least. So we need to end up with y equals x. So here's what we do, and this is tricky. Well, we know that 0 is true for any of them, right? So in other words, anything plus 0 is the anything, right? So in particular, what if we start with x? Well, that's x plus y. What's x plus y? If x and y are, if y is the 0 vector, what's x plus y?
X.
X. Okay, on the other hand, x plus y is equal to y plus x. Do we know that's true, by the way?
Yes.
Yeah, commutative property is one of the 10. But what's y plus x? If now x is a 0 vector,
Y.
that's equal to y. Okay, now we have x plus y is x, and x plus y is also y. So now what can we say?
Therefore, x and y must be the same.
Yeah, x equals y, and therefore 0 is unique. Because if I found 2 of them, I found out they were the same. So it's like really hard to come up with a proof of something so obvious. Do you agree? Okay, what's the next thing I have to do? How about number 2? I want to show that negative v is unique. Okay, now what is the definition of negative v?
B plus negative B equals 0.
Yeah, so we know that v plus negative v is equal to 0. Okay, but let's do this again. Again, what we're doing is we're trying to show uniqueness. So let's call it v plus x equals 0. So let's write if v plus x equals 0 and v plus y equals 0. What's my goal?
To show x and y are the same.
Yeah, to show y equals x. Any questions on that? Okay, well, what can I do? We need to get a y equals x.
Can we just use the same proof from last time, or?
But we know 0 is unique. So when you say the same proof, what do you mean? Okay, so let's try it. So you want to go x plus y.
Yeah.
And then what?
Equals x, or?
No, that's only if y is 0. Y is not 0 here. Right? Let's say V is a 2 by 2 matrix, 1, 2, 3, 4. Then y is -1, -2, -3, -4. So x plus y is not x. Is that clear?
Would it
Yeah.
be in this case negative 2x? Or do we not know it's negative at this point?
Yeah, we don't even know that yet. That's number 4. We still got to prove that. So you got to be careful about proving. You can't use number 4 to prove number 2 if you haven't proved number 4 yet. Is that clear? Okay. So again, you can write x plus y, but is that going to do it for us?
Yeah, on second thought, probably not really.
Well,
Okay.
if we know that 0 is unique and there's only 1, then we could set it equal to each other, right?
Right. We could say v plus x equals v plus y, but we're going to run into the same problem we ran into before.
Yeah.
See, we got that. See, we got there, and then we didn't know what to do because you can't cancel.
Mm-hmm.
Okay. So that didn't work. So you need to get this uniqueness of negative v. So again, you start out with v plus x equals 0 and v plus y equals 0. Any ideas?
X plus B equals 0, right?
What's that?
X plus B equals 0 as well.
Yeah, okay, so let's write that down. X plus v equals 0. We know that's true by the commutativity property, and that's a property. Again, we're only allowed to use properties. So now what does that tell us? Again, we need to get somehow x equals y, right? So should I help you? Okay, so what can I do here? Has to do with a 0. We need to somehow we need to look at the 0. What do we know a 0 is equal to? 0 is v plus x. It's also equal to v plus y, right? Any questions on that? So we do know that what? What is v plus 0?
That's B.
That's v. Keeps wanting to be capital. But what's 0?
V plus x or v plus y.
V plus x. So that's v plus x. Any questions on that? But it's also equal to what? What's v plus x?
2v plus x.
V plus x.
Yeah, you can write it as 2v plus x if you want. Okay. So we're getting there, but we're not quite there yet. Because does that do it to us, for us? Any thoughts? Because again, this is tough, right? I kind of wanted to show you how tough this is, even though it's so obvious. Well, of course, negative v is unique, right? It's got to be, right? So how do you show it's unique? So we're gonna look at that. Well, what can we do? Why don't we subtract the 2 and see what we get? Okay. What is x minus y? What's x minus y? Any thoughts? What's x minus y? Well, x is x plus y, right? So x minus y is the same thing as x plus y minus y. Any questions on that? What's x plus y minus y?
Just x.
That's x. Any questions on that? Well, that's a problem, right? So what does that tell you that x, so that means x minus y is x. What does that tell you y must be if they were different? What does that tell you what the minus y is?
Minus x.
No, if x, see, x minus y is x plus negative y, right?
So Y must be 0.
Yeah, y must be 0. But if y is 0, then v is 0. Any questions on that? Because v plus y is 0, so v must be 0. But if v is 0, x is 0. So what does that tell us? That means that X and Y must have been the same. Any questions on that? We kind of assume they were different. Let's look at number 3. All right, now we have 0v, and we need to get 0 when we're done, right? So any ideas? We need to get the 0 vector. And remember, the 0v means the 0 number times v. Okay, again, these are like really obvious, except then you try and prove it, and it's like, huh, now what do I do? Well, what does it mean to say 0v? We need to show it's equal to the 0 vector. What does it mean to be the 0 vector?
That when you add it to another vector, it does not change it.
Right. So I'm going to add it, not just to any other vector, but I'm going to add it to 1 times v. And see what I get. Now, if it's a 0 vector and I add it to 1v, what should I end up with, by the way?
1v.
1v. That's what I need to prove. Okay, now what property can I use? Here's a hint. Starts with a D.
Distributive.
Yep, I can use the distributive property. That's 0 plus 1 times v. That's the distributive property. Now 0 and 1 are numbers. What's 0 plus 1? You better all know.
1.
That's 1. And that's the whole proof. So then that tells you 0v is the 0 vector. Any questions on that? Okay, then finally, negative 1v, we want to show that's equal to negative v. Well, basically, that's the same thing. Proof of 4. What I need to do is I need to take negative 1v, and I need to add it to v, and what am I supposed to get?
0.
0, and that would mean that negative 1v is the negative of v. Okay, the additive inverse of v. But I can write v as 1v, because that's what 1v is. That was one of the properties, actually, if you remember. In fact, let me write it as with an equal. Equal negative 1v plus 1v. That was a property. And now what can I do?
Again, use the distribute property.
Yep, distributive again. Negative 1 plus 1 v. And if you can't tell me what negative 1 plus 1 is, you don't belong in this class. What is it?
0.
Yeah, that's 0 v. But then by number 3, what's 0 v?
The 0 vector.
That's the 0 vector, and I'm done. So I showed that negative 1 times v is the additive inverse of v. Because if I add it to v, I get the 0 vector. Any questions in this theorem? All right, so the good news is now that I've proven all these for you, now you can use them. Okay, but you can't use like 0 times v is 0, which is so obvious. Can't use it until you've proven it, and now it's been proven. Okay, here comes the next one, which you guys were talking about. And that is if u plus v equals u plus w, then v equals w. Okay, now you look at that and you say, of course, right? It's got to be, of course it's true, right? Is that your feeling?
A little
Yes.
bit.
Okay, is that a proof?
No.
No. And that's what makes proofs hard, is that sometimes it's just so, it's like it has to, of course it's true. That's not a proof. We actually have to use the properties, okay, or anything we just proved, because once it's been proven, then you can use it to show this is true. So we need to say if u plus v equals u plus w, then v equals w. Okay, so we need to somehow get rid of the U. Any questions on that? All right, well, what I can do is I can start out with V. That's typically what you do is you start with the left-hand side and we try to end with the right-hand side. Do you agree? Can't just write V equals W. But what I do know is that V is equal to V plus 0. Do you all agree?
Yes.
Okay. What's V plus 0? What's another way of writing 0? And the hint is I need a U plus V out of this. Because I
V
need to
plus
use
0 U.
what's that?
V plus 0 U.
Not V plus 0 U, but what's another way of writing 0?
-1 plus 1.
Actually, that's not 0 because this 0 is a vector and your 0 is a number. The key is we need to get a U plus V. I have the V. What don't I have now?
A U.
Right. So how can I add 0 and get a U in there?
U minus U.
Yep, U minus U. That we can do. Any questions on that? All right. So we're getting there. All right. Now what's V plus U?
V plus W.
Yeah, that's
U plus W.
U plus W. So that's going to be U plus W minus U. But what's U plus W minus U?
It's just W.
That's W and I'm done. There's the proof. I guess that's the right word, proof. Okay, these proofs are easy to watch. They're really hard to come up with. Do you agree? So you have to I'm going to add 0. And it feels like, why would you think to do that? And the idea is it's the only thing I can do. There's really nothing there for me. Any questions at all on the proof of this theorem and what this theorem is? Okay, so now it says that if you have a vector space, you can do what you want to do. You can cancel. Canceling is a good thing, right? Okay, you can cancel that, and we're going to be doing that a lot. And now we know we can because we have this theorem proven. Okay, now comes kind of a review of what we did the first couple of weeks of class, but not really. Okay, even though it's exactly what I wrote in week 2, I think it was. And that is the following. The definition is the following. A linear combination of the vectors v1, v2 through vk is a vector in the form c1, v1 plus c2, v2 plus ... plus ck, vk. Does that look familiar?
Absolutely.
Yeah, in fact, I wrote this in exactly the same wording. I'm not sure if I put the 2's in, but basically exactly the same wording in week 2. But in week 2, why was it different than what we're doing now?
We weren't talking about vector spaces.
Right, we were doing a special case of a vector space. We were only looking at vectors in Rn. And this now is a definition for general vectors, whether it's Rn or M2 by 3 or P5 or all functions. You can still talk about linear combination. Any questions on the idea? Okay, so for example, let's suppose let V be the vector space of functions. Okay, which last time I proved that that was a vector space, right? or at least I proved part of it. Okay. Then let's do an example. Let's suppose we have f of x is equal to sine of x. And I think I need to write this as an equation. G of x equals e to the x. Okay, give me an example of a linear combination of f and g. So give me an example of a linear combination.
Would it just be some constant times sine of x plus some constant times e to the x?
Give me a specific example.
5 and 4.
Okay, so 5 sine of x plus 4 e to the x is a linear combination. How about sine of x times e to the x? Is that a linear combination?
No.
That's not a linear combination because that is not a constant times sine plus a constant times e to the x. Okay, so you really got to stick with the definition. So 5 and 4 work great. That's a constant times sine plus a constant times e to the x. Any questions on the idea of linear combinations? Okay. By the way, where did we use this? Actually, with probably I guess with me, where did we use this a year ago? Don't you hate when I say that? Around 14 months ago. And you remember? I know it's a long time ago. Huh?
Would it be Lagrange multipliers?
No, that was more like 10 months ago, or maybe 9 months ago. 14 months ago was January, by the way. And you didn't know what a Lagrange multiplier was in January of 2020. You didn't even know what COVID was.
Would it be trig sub?
No, and in fact, we didn't know trig sub in January. That was more February. And that wouldn't be linear combination stuff. Very simple. Integrals. Is we learned that if you take an integral of a linear combination, then you can break up the pluses and pull out the constants. Do you remember that? So we talked about linear combinations of functions when you integrated, because if you had a linear combination of functions, you can break those up. And that's kind of the main reason why we talk about this stuff, is so we can do stuff with it. Okay. And by the way, we will learn in, I think next week, that an integral is a linear transformation of the vector space of functions, of integral functions. Okay. Just to let you know, we'll talk about that next week. So we'll do that kind of calculus. And so is a derivative, by the way. Okay, the next definition. The span, have you heard that word before?
Yes.
Yeah, have you heard it applied to a general vector space before?
No.
The answer is no, you only applied it to vectors in Rn. And the idea is we can take the exact same definition and apply it to a general vector space, and it still works. So the span of a set of vectors, v1 through vk, is a set of all linear combinations of these vectors. Isn't that the same definition that we had? Okay, it's just perspective, but now the perspective is v1 through vk don't have to be vectors in Rn, they could be matrices. And you could talk about the span of a couple matrices. Any questions on that idea? So I'll do an example. The span of, now I got to pop in some matrices. Actually, I need a bracket first because we're doing a set. So the span of the set there we go. Ah. One, 1, 0, 0, 0, 1, 1, 0, and 0, 0, 1, 1. Okay, so the question is, so let's look at span of that. Let's call it S. So let's S be the span of these three vectors. Okay, so you got to get used to the fact now we can say that this matrix is a vector because we said that 2 by 2 matrices, a set of 2 by 2 matrices is a vector space. So what is this? So we can talk about what is the span of these guys. So the question is the matrix 1, -1, 0, 2, in S. How do we decide? So what do we have to do to find out if the matrix 1, -1, 0, 2 is in the span of the set 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1?
We need to find if there's a linear combination that forms that vector.
Right. Exactly. We need to see if there's a linear combination. So we're going to do, just to save a little time, and copy and paste. And I'm going to say we're going to take C1 times the first matrix plus C2 times the second matrix plus C3 times the third matrix. And the question is, can we find C1, C2, and C3 that give you 1, -1, 0, 2? Well, how do we decide? Any thoughts? What can we do? Any ideas?
We maybe distribute out the scalars and then like have like C1 plus C2 plus C. Wait, no, hold on. C1 equals 1. Like, you see what I mean there? Like,
right. So what we can do is we can multiply the scalars in, and then we can equate like positions.
yeah.
That's what you mean, right?
Yes, exactly.
Okay. So let's do that. So the first equation is just C1. I'm looking at the top left corner. C1 equals 1. The second equation, actually, let's do it with a comma. The second equation will be C1 plus C2 equals -1. The third equation will be C2 plus C3 equals 0. And the fourth equation will be C3 equals 2. Any questions on any of those? Okay, given there's a linear algebra class, how do I use linear algebra to do this?
Set up a matrix and then RREF it.
Yep. So now it's going to be, actually, it's going to be a 4 by 4 matrix where the fourth column actually is the, it's adjoined. So let's do that.
Don't those kinds of matrices have like a special name? It's like a
Adjoined.
no, I thought I saw a different name for it in the book. It's, let me look it up.
Okay. I need one more row also. All right. So now the first one is just a 1, 0, 0, 1. The second is going to be 1, 1, 0, -1. The third is going to be 0, 1, oops, 1, 1, 0. And the fourth will be 0, 0, 0, 2. Sorry, 0, 0, 1, 2. That's better. Any questions so far? And what do I do?
RREF.
So we're going to RREF this. And again, there's lots of ways of RREFing it. Let me, like I said, you can put it in Symbol Lab. I think this one's not too bad. I'll find out in a minute. I made up the numbers as we were talking. But I can definitely take the first row times -1, add it to the second. That makes that one a 0. And then that makes that -1 a -2. Any questions on that? Then I could take the second row, multiply by -1, add it to the third. So this guy becomes a 0. That one stays a 1. This one becomes a 2. Any questions so far? What can I do next?
Eliminate the last row.
Yeah. So I can subtract I can add -1 times the third row and to the fourth row. And that last row becomes 0 and 0. And what do you see? Is there a solution? So now we're back to the first week of class.
Yeah, there's a solution.
Yeah, there is. So now what is the answer to, is this matrix in the span of S?
Yes.
Yes, it is. Okay. So the answer is yes, because we got a solution. Whereas if we got no solution, like if you got if that bottom row were 0, 0, 0, 5, that would be no solution. And then you would say it's not in the span. Any questions on that? So you get the idea of span. It's the same as before. And eventually you get matrices. When are you not going to get a matrix if you're talking about span?
With just numbers?
Well, you'll get a 1 by 1 matrix, but those are boring. Okay, functions. So for example, if you look at all possible combinations, If you look at all possible combinations of sines and cosine of nx, where n is an integer, and you want to find is x squared in the span of that, you can't do it with matrices. Does that make sense? Because you're going to have an infinite number of them. So infinite by infinite matrices don't work, just let you know. So that's the example where it won't happen. I'm not going to do one now today. Okay, then finally, our last definition is let V be a vector space. Then we say that the set S equals V1 through Vk spans V. Sometimes you'll also say is a spanning set for V. If every lowercase v and capital V can be written as a linear combination of vectors in V. That is, every V can be written as C1 V1 plus ... CK VK. Is this any different than the definition that we had in the third week of class? I think third. Might be second week. Any different than the definition of spanning that we had before?
No.
Yeah, the only difference is perspective. Okay, every word is exactly the same. What's different is perspective. Before, V were vectors in Rn, but with this definition, V are just vectors in a vector space. They could be matrices, they could be polynomials, etc. Does that make sense? Okay, so for example, does, and now I need to get an equation. Does the set x squared plus 3x, comma, 2x minus 4, comma, 2x squared minus x, let's see, no, plus 5x just a minute, plus 4 span P2. Any questions on the question? Make that a 4x, sorry. Okay, so does that span P2? What do I need to do?
Find a basis.
Okay, so what's a basis for P2? You can find a basis, but we don't even know what the word basis means yet. We don't have the word basis for P2, do we?
No.
So good luck finding a basis when we don't know what a basis is. We don't know what that word is yet. We'll get there, but we're not there yet. We can only use the definition. That's the hint.
Write it as a linear combination of vectors.
Yeah, or actually see if we can write, not it, but see if we can write a general polynomial in P2 as a linear combination of these three vectors. Any questions on the idea? What does a general polynomial in P2 look like?
X squared.
Actually, ax squared, make it real general.
Ax squared plus bx plus c.
Yeah, bx plus c. You've been doing this like since you learned the quadratic formula, right? And the question is, can that always be written as c1 times x squared plus 3x, and then plus c2, oops, c2, and then times 2x minus 4, and then plus c3 times 2x squared plus 4x plus 4. Oops, I need parentheses. Any questions on the question? All right, what can I do now? Here's a hint, algebra, basic algebra.
Distribute and then combine like terms.
Yeah, and hopefully you're advanced enough that you can do those in one step. So what I'm going to write is that so I can write that as C1 plus C2, C3 is equal to A. And then I have 3C1 and then plus 2C2 plus 4C3 is equal to B. And then I have negative 4C2 and then plus 4C3 is equal to C. Any questions on that? How can I nicely rewrite this given the class we're in?
As a matrix?
Yeah, I can write this as a matrix equation. So let's do that. So it turns out all the stuff that we did for Rn is also going to work for Pn and n by n, and vectors. It's going to work for all the stuff we've done as long as it's a finite dimensional, it turns out. So now what I can do is I can write the matrix. So we have C1, C2, C3, we have 3 by 3. And the first one is a 1, 0, 2. We have 3, 2, 4. And 0, negative 4, negative 4. And we want to multiply that by our C1, C2, C3. And see if we can get everything, ABC. And ABC it means everything, any choice of A, B, and C. I lost it one more time. Let's just do this. Okay, so when is there always a solution? Now it's going back to, a month ago. When is there always a solution to this kind of equation?
If there's an inverse to our matrix.
Exactly. So if there's an inverse to the matrix, there's always a solution. But if we care about whether there's an inverse, that means we can use TFAE. And what's the easiest of the TFAEs that I can actually do in my head with some work? I probably won't do it in my head. I'll probably just write it out.
Probably the determinant.
Yeah, let's take the determinant and see what we get. So we get 1. I'm just going to go by the first row because it's got the 0 in it. So 1 times the determinant of the minor, which is -12 minus -16, which is 4. And then we're going to have plus 2, plus 0, but I'm not going to write the 0, plus 2 times. And now I'm going to get what?
-12.
Yep, -12. And all that matters is this 0?
No.
Right, is not 0. So what does that mean?
There's an inverse.
Yeah, so there's an inverse. Looks like I might have made a mistake though, because I think I tried to make it not have one. I probably should just look at my work and see if I made a mistake somewhere. So C1, x squared plus 3x, C2, 2x minus 4, C3, 2x squared plus 4x plus 4. Just double checking. So we have a C1 plus 2C3. That looks good. We have a 3C1 and then 2C2 and 4C3. All those are positive. And then we have a -4C2 and a 4C3. Ah, there we go. I knew I missed something. That negative is a positive. So let's try it again. Sorry about that. So now what do we get? Now we get 12 minus a -16, which is what?
28.
28, 16, 12 is 28. Uh-oh. I thought I made this not work. I mean, get 0, but let's see. And then 2 times -12. Still is not 0. Okay. Well, for now, I'll just say it's not 0. But I thought I wanted to make it 0. So what does that tell you? If it's not 0?
This is a linear. This does span it.
Yeah, then it does span. Okay. But you could check my work. If I made an arithmetic mistake, I apologize.
If we were to get a determinant of 0, this would not span P2, correct?
Exactly. Okay, so that's all I have to say about the homework that is due on Wednesday. Other than one more thing I want to say, in that the stuff that's due on Wednesday is not on the exam. Got it? Okay, but it definitely is, could be on the final exam, but it's not on your exam 2. Okay, what I did want to do, just a second. That one. There we go, just a second. As I want to start talking about the exam. So in particular, I need to share my desktop as the syllabus. And I want to go back. Okay, so exam 1 was on February 3rd. And then notice chapter 5 is what happened after then. And you had 5.1 through 5.6. Sorry, 5.1 through 5.9. And then you had 7.1 through 7.4. So the exam 2 covers chapter 5 and chapter 7. Any questions on that? Okay, I want to let you know that the rules of the exam 2 are exactly the same as the rules of exam 1. So what does that mean? What do you expect is going to happen?
First problem is going to be without computer, and then the other ones we're going to be allowed to use our computer.
Yep. So the first problem will be without computer, and then after that will be, with computer. And in particular, what's the kind of when you see the exam, how are you going to find the exam?
It's going to be
On Canvas.
assignments. Yeah.
Yeah. You're going to Canvas, you're going to go to the assignments, and then it'll be under, see the submit button? You're going to click the submit button. Right now, if you hit the submit button, nothing happens. But when you go to the assignment, then I'll post it just before the exam starts. So I'll post it probably around 12:59 or ish, plus or minus 1 minute. So basically, I'll post the exam just as the exam starts. So then you can go in and take a look at the exam. Okay. As I mentioned, it's pencil and paper, just like exam 1. So you're gonna take paper and you're gonna write out. You do not have to write down the questions. You only have to write down your work and the answers, just like exam 1. And then you're going to take a picture of your paper. Okay, trust me, you do not want to do your exam by typing about all the stuff on the computer. It'll take way too long. Trust me, because guess what I did this morning?
You wrote it on a computer.
I typed it. Yeah, I did. I wrote the key, and it took me a long time to write the key. Not because I need to think a lot. It just takes a long time to type matrices. But if you write it on a piece of paper, that's not so hard. Do you agree? It at least doesn't take as much time if you know what you're doing. So that's just a note. You can do it on a piece of pencil and paper, or pen and paper. That's fine too. And then you're going to take a picture using your smartphone, and you're going to post the exam in the submission, just like you did for exam 1. Any questions on the process?
Does it have to be a PDF file, or can we submit it as a JPEG?
Most important thing is I can open it. So if I've been able to open your homework and read it well, I would recommend doing that. Does that make sense?
Yeah.
So my recommendation is whatever's working for your homework is what you should do for the exam, because that's what you're used to. You know it works. And if I can't read it, then I let you know I can't read it when it's homework, which hasn't happened much. Okay. Imagine if this pandemic happened, 30 years ago.
That would have been a real bummer.
Right. Actually, it wouldn't have been a bummer for most of you because you wouldn't be alive, right? But the point is, if you were alive 30 years ago taking this class, it would have been a real bummer. So the good news is we have technology. Okay, so we can do it. Okay, and it seems like you all have the ability to take a picture, which is good. Okay, so any questions on the process of the exam? Okay,
Yeah, I have a
and
quick question.
yeah.
Last exam I stopped about 10 minutes early at like 2:35 to scan it in because I didn't want to turn it in late. Would you rather have us do that or go to the full 2:45 and then take like 5 minutes to submit it?
I'm kind of flexible. If it takes you 5 minutes to submit it, I'll let it fly. Do not tell me it took 7 hours to submit.
Got it.
Yeah, so as long as you're honest, and whether you like it or not, I'm going by the honesty principle for this for this class, is that you need to learn this material. It's not just the grade. The grades, as I mentioned, is not that important because most of you have already applied to your university. They're not going to ever see this grade. Okay, you need to pass. But if you don't learn this stuff, you're gonna get hammered next year when you take your advanced courses. Does that make sense? So the real reason to study a lot is to learn this stuff. And I'm hoping, you guys are second-year calculus students. You're mature enough that you can do that. Okay. So I do want to let you know a few things. Let me talk about some of the content now that I've talked about processes and stuff like that. And that is, again, it's chapter 5. So let me go through and tell you what 5 is. What was 5 all about? Since it's right in front of you, if you're looking at the screen.
Linear transformations.
Linear transformations. So I want to remind you, because it's been a while since you might have thought about them. What do you have to do with a linear transformation? You have to be able to show something is a linear transformation. Do you remember doing that? What's the process of showing something a linear transformation?
It is closed under addition and under multiplication.
Exactly. Okay. You have to be able to find the matrix of a linear transformation. Okay. And that could be from different bases. So you could have a weird basis for R5 and a weird basis for R2. And then I give you the linear transformation, where it sends, the standard basis, and you got to be able to figure out where what the matrix of the linear transformation is with respect to the strange basis. Does that make sense? Okay. Then there was the one-to-one and onto and isomorphisms. Do you remember the image and the kernel? So what is an isomorphism, by the way?
It's 1-to-1 and it's onto.
Yeah, so isomorphism means one-to-one and onto. So in particular, if it's an isomorphism, what do you know about the kernel?
Equals 0.
Equals 0. Okay. And what do you know about the image? And don't tell me equals 0. The image is equal to the range space. Okay, equal to the basis. I'm not sure you mean by the basis, but the image of the linear transformation must be equal to the entire range. So if the linear transformation goes from R2 to R5, good luck getting an isomorphism, because you're not going to send R2 to all of R5. You're going to miss something. Okay, so you need to be able to find the image, and you need to find the kernel of a linear transformation. Any questions on that? Okay, and I will let you know that other than question number 1, for the rest of them, you are expected to be able to use a computer. Okay, I did not work hard to make the numbers beautiful, because I figured outside number 1, which does have beautiful numbers, by the way, outside number 1, you're going to use a computer and pop it in. And if it gives you fractions, I don't feel guilty. Are you okay with that?
Yeah.
Okay. But what I do ask is that you show what you put into the computer and describe your linear algebra, I RREF'd, that kind of thing. Does that make sense? So just write down what you're doing. Okay, don't just put a box around the answer, but write down how you got there with the computer. Any questions on chapter 5? Okay, then came chapter 7. Okay, and chapter 7 was all about eigenvalues and eigenvectors. So as I think one of you mentioned, question number 1 is you're going to have to diagonalize a matrix. Okay, and what I mean by that is you're going to find eigenvalues, you're going to find eigenvectors, you're going to have to write down the diagonal matrix and write down the P matrix. Does that sound fair?
Yeah.
And I will guarantee that if you do it in the kind of logical way, all the numbers will be nice. Okay. Okay. I made it really beautiful. Okay. But it is a big matrix. I'll let you know that too. Okay. So there's a lot of writing, but all the numbers are nice. There's a lot of zeros, which means that everything's good. So and I made it so that if you use a computer, it's going to do it the hard way with messy and horrible. And I won't give you points for that. You have to do it the way you would do it by hand. Okay. But you also should know how to use a computer to remember, you take a minus lambda I, and then you take the determinant, and then you get a polynomial, and you set the polynomial equals 0, and you solve. Okay, so again, you have to write down what a minus lambda I is on paper. You have to write down what the characteristic polynomial is on paper. Okay, but you don't have to actually, do the determinant. You can let the computer do that. And you don't have to, find the roots using, hard factoring and synthetic division, all that. Let a computer do that. Is that clear?
Wait, so on the first problem for the characteristic
No,
polynomial,
not the first problem. Not the
Okay.
first problem. Talking about all the rest of them.
For the first one, we'll have to factor. Okay, cool.
Yeah, the first problem you'll have to factor, but I promise you that if you sit there and look at it for a bit and you factor it like nicely instead of like multiply a whole bunch of mess through and then try to factor, it'll factor beautifully and it'll take less than a minute to do. Okay, but if you do it the computer way, it won't. It'll be complete mess. Okay, you should know how to diagonalize. Do you remember how to diagonalize? What do you have to find?
The eigenvalues and their corresponding eigenvectors.
Exactly. This chapter is all about eigenvalues and eigenvectors. Okay, what applications do you have to know?
Taking the power of a matrix.
Yep, you should know how to take a power. What else should you know how to do?
The probability matrix.
Yeah, probability matrix and the steady state vectors that correspond to it. Okay, remember, if you have a probability matrix, what do you always know an eigenvalue is?
1.
1. So in other words, don't go try and search for an eigenvalue. You know it's a 1, right? Okay. What's the last application we did?
E to the A.
I think that was the second to last.
Fibonacci sequence.
That was the third to last. So those are important too. I was going to mention those too. Conics. I think that was last, unless my brain is in the wrong order. Remember conics? So you should be able to do conic sections. You should be able to do Fibonacci. You should be able to do E to an A. Okay. Any questions on that? So I will tell you, I believe I put 2 applications on the test. Okay. The last problem has 4 parts, and each part is worth 2/3 of a regular problem. So it's a big part. And what do you know that I always give those of you who had me a bunch of quarters already?
True and false.
True or false. And in this class, it's true, false, and prove. Okay, so if it's false, all you have to do is find one example that doesn't work. If it's true, you have to do a proof. Any questions on that? So the falses are easier than the trues. Okay, so that's the exam. I'm looking at the clock and we're over. Try not to go too much over, but it's 2:48. So I'm going to stop the share. And I'm going to stop the recording.